So looking at parametrics, there's a couple things that we need to talk about. I'm going to try and give you guys the best overall understanding that I can of parametrics. And then if there's anything that you guys are lost on, please do stop me and tell me like, hey, I don't know what you're talking about. And then we're going to try and talk about it a little bit in detail. So parametrics are a very ingenious way of representing curves with a time parameter. Okay, so currently we've been dealing with functions that have two variables. We've been dealing with functions that have an x and a y variable. Now, obviously we live in a three-dimensional world, so we can introduce a third variable. We can either call it the z-axis or we can call it the time axis. So we can see, like, for example, there is types of functions that change in x and y, but also in t. So for example, if you guys think, like Emma, when you do physics, and Tarek, it's a very simple example, when you throw a ball, right? You know for a fact that there is like when you do the, what are they called again? Equations of motion, right? And they're like the Suvat equations, right? And you have change in position in x and y, but then you also have time as a parameter. And so not only do you know that the function looks like a parabola, obviously, so when you throw a ball, for example, let's show you everyone this example. So if I get like a catapult or something out here and I launch a ball, I have this like pink ball and I launch it into the axis. Yep. So a ball gets launched and we're going to end up with something like this. We're going to have a parabola, it's going to peak somewhere and then it's going to fall onto the floor. Everyone cool with this? Now, obviously, we have an xy relationship. We have an xy relationship of a parabola. That's very clear. But what about, okay, this is really annoying. I'm just going to leave it as dotted lines. Everyone gets the point. We have xy relationship. So we have like our x and our y. But we also have time. I can ask a physics student what happens at this time. So I can ask a physics student what happens at t equals 0. And at t equals 0, the x would be like negative something. Actually, let's just make this a lot simpler, just so that we don't have to think about negatives. Let's just move the whole catapult right here. So the moment it starts launching, it launches from the ground. Not the ground, but like the highest point of the catapult. It launches some amount. At t equals 0, we can say that the ball is at whatever this y value is. So x value is 0, t value is 0, and y value is, I don't know, let's just call it y, 1. Okay? Then we can say at the highest point, let's call it t equals 3, we can say, okay, maybe after 3 seconds of the ball launching, it's now has a height of y2 and x position of, I don't know, x1 and whatever. Okay? So we can see this, the whole point of parametric functions is there a mathematical way of allowing us to represent functions that have more than just two parameters. So x, y, most of the time we're talking about time, but you can introduce any other parameters that you want. Okay? So I'll write that down in a little note for you guys in the notes, and then we'll just start doing a bunch of examples so I can show you guys how it works. What I've written here is that the way we represent these parametric functions is we have two separate equations for each coordinate, okay? So the x coordinate is going to have its own equation in terms of time, and so will the y coordinate. So they will each have their own separate equation, which is a bit different to what we normally do. So I'm going to write you guys, so we've seen the normal table of values where we have x and then we have y, and we plug in x values and plug in y values, right? Now what I'm going to do is I'm going to show you guys an example of a table of values, because everyone agrees table of values is like the first most simple thing you meet when you look at like linear equations, for example, right? So now I'm going to introduce parametric functions in the most simple and understandable way that I can. So I'm going to show you a parametric form of a function. So a parametric function will be something like this. So I have maybe my x will be represented on its own in terms of t, so 16t maybe. And then my y will be represented on its own in terms of t. So I might say y is negative 5t squared plus 25t. Let's make a table of values for this. So what is the variable in both of the equations? T. So that's the thing we're kind of plugging into everything. And then our quote unquote outputs are both x and y. So we want to know what happens to both x and y as t changes. So let's plug in like 0, 1, 2, 2.5, and I don't know, 3 or something. Okay, let's plug all of those things in. So can I get maybe, Tyrick, can you do x, and Emma, can you do y? And then we will come back and see what happens. Okay, so Tyrick, what did you get for the x's when you plugged in 0?
0,
Mm-hmm.
16,
Mm-hmm.
32,
Mm-hmm.
40,
Mm-hmm.
and 48.
Cool. And then Emma, what about for the y's?
0,
Mm-hmm.
20,
Mm-hmm.
30.
Yep.
31.25.
Yep.
And 30.
Cool. So now what we're going to do is we're going to graph this. So we're going to plot each of these points and we're going to graph them. So x and y start at 0, 0. So this is the x and this is the y. So x and y start at 0, 0. Then we have 16 and 20. So 16 on the x, 20 on the y. That's our next point. That's our t equals 1 point. Then we have 32 and 30. So somewhere here, 32 and 30. And that's our t equals 2 point. Obviously this is not to scale, so you guys are going to have to bear with me a little bit. And then we have our next highest point is 31.25. So it's going to be like somewhere just a little bit higher here. And that's going to be at 40. And that's our t equals 3. And then it starts going back down, as we can see by the y value. So it goes back down to 30. So in line with this next one, and that's our 3. And so this, again, is an example of a ball being thrown. Okay, and we can see that as time increases, we can see what's going to happen. Obviously, the ball's going to keep falling. Okay, now that is... oh, sorry, that was time supposed to be 3. This should have been 2.5. This should have been 3. This should have been 48. And that is... I'll move 30 down a little bit. And that's 31.25. Okay. Everyone cool with this? So that is the most basic example of a parametric form. I've shown you guys that we represent the actual x and y variables as 2 separate equations now. And then we have them in terms of t, which is our time variable. It is still just plotting a function, but we're including this extra piece of information, which is time as we graph it. Okay? So now we're going to look at how do we convert, because obviously when I give you this, unless you were to do a table of values, it's not extremely obvious how you would graph this, right? It's not the most obvious thing in the world. So what we're going to do is I'm going to show you guys how to convert a parametric function into just its Cartesian shape. So it's Cartesian shape on the normal xy plane without taking time into consideration. But before we do that, I want to show you guys how to play around with parametrics on Desmos, just because it does kind of increase your awareness of how they work. So I want to take a pause for a second and do that. So to graph parametric stuff, what you need to do is, you know how I was before using like lowercase y and lowercase x? So Desmos has a special form for parametrics where you have to use capitals. So you just use a capital X, and then you use the lowercase t, and then it immediately gives you the ability to pop up the t as a slider, which is what you want, because obviously you want to be able to change the time. That's the whole point of sliders in Desmos. They allow you to change. So I might type in a function, like I'll give you guys like a really ugly parametric function. So 3t plus pi on 4. Yeah, whatever, let's just do pi on 4, that's fine. And then we're also going to do, now what you need to do, obviously you don't want to see the Cartesian version of this function, so what you're going to do is you're just going to uncheck it, so you don't want to be able to see it. You're going to do the same thing for whatever the y function is. So I'll quickly write down the y function, and then I'll show you guys how to get the parametric form to pop up. To be extra clear, Desmos will still graph the functions in Cartesian form because it is still a Cartesian equation. But because we want to represent it in parametric form, you just want to not show those two functions. Instead, what we want to do is we want to show the x function as a coordinate and the y function as a coordinate. So what we're going to do is we're going to plot a coordinate system, and our coordinate system will be our functions. Does that kind of make sense? Because that's the definition of a parametric function. So remember how I said like the x coordinate will have its own equation, the y coordinate will have its own equation, and then we see how the coordinates change over time. So what we want to plot is we want to plot the y and x coordinate over time. And you can see that if we add a slider for t, I don't know how to add sliders in Desmos, which is, maybe if I do like p of t, yes, good. Okay, nice. And you can see the cool thing is it shows you the graph moving over time. Does everyone see that? So if we move this really fast, or if I just kind of play this, we can see what it is. It's just like a little point and it moves around. And obviously it's moving around y because we're moving t. As time changes, so does the coordinate. Does everyone understand that? And so we can graph what we had before. So what did we have before? We had like the ball moving. So it was 16t. 16t. And then we had negative 5t squared plus 25t. Negative 5t squared plus 25t. Cool. And then same thing, so I might just have to zoom out for this one. And we should be able to see it somewhere, I'm assuming. Yeah, there we go. Okay, so we can see obviously now it's not super realistic for a ball being thrown because obviously the ball shouldn't be able to go into the ground. But I can also limit it, so I can say t has to start at 0. So at the moment my t goes up to negative 10, but that doesn't make sense obviously, right? So we're going to start our t at 0 for the ball being thrown, and we're going to see what happens as time goes to like 10, for example. And you can see it's just literally like a ball being thrown. Okay, so even when you're studying physics, and we can see it intercepts at like, where does it intercept? At around 80. So we can say that I think we've got to decrease time a little bit more, maybe to like 5 and see what happens. It's going slower now. Like, hurry up, my dude. Yeah, so we see it kind of goes down and then comes back up. So the cool thing about this is, like, for example, when you're studying physics, if you ever want to like visualize what the projectile looks like, you can just chuck it into Desmos like this and actually see it moving. Okay, and if you guys want to see just the Cartesian form, so sometimes questions, and you guys are going to see the questions in a second, sometimes the Cartesian form will ask you to just the question will ask you to show the Cartesian form of a parametric. So if you don't want to visualize it as this animation on Desmos and you just want it to graph what the graph looks like you want to graph the path, you just don't include a slider and you just tell it where to go up to, so 5, and it'll just show you the path instead. Okay, so if you do want to see how it changes over time, include a slider and then you can play the slider and it'll show you an animation. If you don't want to include the time and you just want to see what the path is supposed to look like, just get rid of the slider and Desmos will automatically pop up this like 0, like this range for you to put t at, and then it'll just graph the function at that range of t. Everyone understands that? So definitely when I'm setting textbook questions, I would 100% be saying that you should check your answers using Desmos because it gives you a better understanding. I think 90% of the confusion with parametric functions comes from kids actually not understanding what they are doing. But I think literally just the way that Desmos forces you to graph it by creating an x and a y function, and then literally the way to graph the parametric is to make an xy coordinate out of those functions, is literally teaching you what a parametric is. Okay, so it definitely makes it more clear, and I 100% urge you guys to be using Desmos as much as you can during this unit. Okay, so I will save that graph parametrics and I'll pop it into our notes so that you guys are able to How do I share these? Share your save graph copies. Okay, and I'll just put this Desmos here so it's in the notes for you guys. So if you need to view it, you just click that link and it will take you there. Is there a way for me to, let me just double check if I can All right, so that's the most basic understanding of parametric. So now you know what a parametric is. You know how it works as having like the X and Y equations are separate to each other, and then you graph them in terms of t together. And then the next thing we're going to do is we're going to talk about, as I said, how to convert from this parametric form which separates the two equations, and how to convert it now to a Cartesian form where you actually include the equations together as a normal y equals x function. Okay, so let's do that now. So obviously, what is the difference between Cartesian form? So Cartesian form is the normal function form that we're used to. Someone tell me what is the only difference between Cartesian form and parametric form. There's one extra variable and we want to get rid of it. What is it? Time. So in order to convert to Cartesian form, we just get rid of time. We have to figure out a way to get rid of time. That makes mathematical sense. So to convert to Cartesian form, we want to remove time the time parameter. Okay, so how are we going to do this? Essentially, we can literally just do it as though it was, what is another example you guys have seen of this? Like if someone had to take a guess about how we were going to remove time, what does someone think? Simultaneous equations. It's the most obvious thing to do. Okay, so we'll find x first. In order to find x, I'm going to use this equation. So from the x equation, I'm just going to change it into t equals x on 16. And I'm going to now sub t into y. Okay, so now y equals -5 x on 16 squared plus 25 x on 16. Everybody cool with that? And so now we just simplify it. Okay, now simplifying this is a bit disgusting, so I might give you guys this as a little algebra exercise to do in your own time. I'm just going to tell you, actually I might make you do it right now, but I'm just going to tell you what the final answer should be. So there should be some kind of simplifying steps in the middle here. And then you should be able to get down to y equals -5x, x minus 80, all over 256. Okay? And that's where your advanced math knowledge is coming in. Okay, so you need to be able to simplify that, and really the only way you can simplify that is with the algebraic techniques you learned in advanced. So, huh? Oh, well, because I prepare for the lessons in advance, so I did it before the lesson. I didn't do it in my head. All right, so can I get you guys to try quickly simplifying that? Just make sure that you can get down to the same answer. And then we're going to move on with the extension stuff. So in order to do it, you just expand the squared into this bracket. You end up with this, and then you obviously want to make a common denominator, so you want to multiply the top and bottom of the second fraction by 16 on 16. So you're going to end up with -5x squared plus 25 times 16, which is 400x all over 256. And then we end up with sub out a -5 x, and you just end up with x minus 80 all over 256. Okay, so pretty simple algebraic steps. Very important that you guys can do them, because I don't want you to be having issues with advanced algebra. So if you had trouble with it, just do a bit more practice and you'll be fine. Okay, so that is how to convert to a Cartesian form. So now I want to give you guys a couple of questions. Now, I just want to be very clear. When you guys are extension math students, which you all are, you need to make sure that you don't have a caveat at advanced math, because something like this is an extremely easy question. When I ask you, like, convert to Cartesian form, the question itself is very easy. You know what to do. You solve for t in one equation and you plug it into the next. But a question like this would be out of 3 marks. If all you are able to do is just get here, you get 1 mark. You do not get all 3 marks. Maybe you get 2 marks depending on the marking criteria. Maybe they give you 1 mark for this, 1 mark for this. But you don't get the 3rd mark unless you do all this extra work, and all of that comes from advanced. So this is why we always say there's a huge difference between a band 5 and a band 6 student. A band 5 student can get 2 out of 3, which is, good enough. But a band 6 student is the one who's able to get that extra 1 mark. And you can see that extra 1 mark, it is a lot of work, right? It shows dedication in both advanced and extension, which is why people say extension is hard. It's not hard. It's just that you have to be focusing in both advanced and extension, because if you can't do advanced, then you're going to struggle in the advanced parts of extension. Okay, so it's just very important that you guys are consistently studying advanced, so that it's not the reason that you're not doing well in extension. Okay, we want extension to be the reason you're not doing well in extension, not advanced. Okay. All right, so now I'm going to give you guys some questions that ask you to convert parametric equations into Cartesian form. I'll put that on the board now, give it a go, and then we're going to go through some more stuff. So give both of these questions a go. For part A, it's asking you to describe geometrically. That just means graph it and show what it looks like. Okay, so give these questions a go, and then we're going to go through them. To do the first one, to get rid of the P, so in this case, instead of using T as a parameter, they're just using P. So to get rid of it, we're just going to do x on 4 equals P. We're going to plug this into the y equation. So y equals x on 4 squared plus 1. So y is equal to x squared on 16 plus 1. And you could graph it like this. I would say, to be honest, I think it's even easier just to graph it in that form. I think it's the easiest way to graph it. So yes, you can simplify, but I think it's already in a form that's pretty easy to graph. So if you think about it, we have our base parabola, and then you just use graph transformation. So what happens to it? It gets shifted up by 1, and then it gets fatter by 4 units. So it'll kind of look like this. Everybody agrees? Okay, well, it looks like this. Just from our graph transformation knowledge. Everyone cool with that? Alrighty. Nice. So that's the first one, and then I'll get you guys to do the second one. Don't get confused by the sine and cos stuff. It's not too confusing, so you just want to get rid of theta. Now, just as a reminder for you guys, whenever you see a sec, cot, or cosec, always remember to put it as 1 over whatever it is. Remember, it's the reciprocal trigs, okay? Tarek, you might have not been here for that lesson. Do you remember me ever teaching you reciprocal trigs? No? No? So I'll just remind you about what they are. So sec, cot, and cosec are just reciprocal trig functions, and all that means is, do you see how this one, the third letter is C, third letter is T, third letter is S?
Yeah.
So this one is just 1 on cos theta. This one is 1 on tan theta. And this one is 1 on sine theta. So that's it. It's just like reciprocal trig. But as a general rule, anytime you see the reciprocal trigs, you should immediately get rid of them. Like, put them as a fraction. Does that make sense?
So I should make it 1 on cos theta?
Yeah, so I would say x is equal to 1 on cos theta, and then y is equal to sine theta, and then go from there. So see if you can eliminate theta. Okay? So trig equations, trig parametrics are always the ones that catch students off guard the most, because you do need to know some trigonometry stuff. So Emma did what most students do, which is you did this. You did theta equals sine inverse of y. And then you plugged theta back into x. So you said or maybe you did it in the reverse order. So maybe you did multiply the cos over. So you would have gotten cos theta equals 1 on x. And then maybe you did theta equals cos inverse of 1 on x. Yeah? Now, I want to be clear, this is mathematically, it's not wrong, right? Mathematically, this is not incorrect. So I can now write y equals sine of cos inverse of 1 on x. And while it's not mathematically incorrect, We all agree that there is no chance in hell anyone's graphing that. Yes? Like, it's not a graphable equation. And I wouldn't even go as far as to say that it's in Cartesian form. Like, it is, but it's not really a useful equation in that form. So what we can do instead is we want to try and eliminate both theta, and we want to eliminate the cos and sine functions as well. We want to just try and get rid of them. So there's a couple things you have to learn. So I'm going to kind of give you guys a little like trig interim just to teach it to you. It is advanced math, but again, you need to know it. So a little like trig interim. Okay. Now, here's some things you guys need to know about trig. Couple of the most important kind of like, I guess, trig identities that you guys need to know as extension math students. It should kind of come to you as being very, very obvious, and I'll explain why in a second. So everyone remembers when I taught you guys trig, I taught you that this coordinate is cos theta sine theta. Everybody remembers that? Yeah? Tarek, you remember that? And you also remember that I can call this whole distance just sine theta, and this whole distance I can call it cos theta. Everyone's on board with me so far. We also remember that this radius is 1. Yes? Tarek, you remember all that?
Yeah.
Yeah. So now, can someone tell me if I wanted to write tan in terms of sine theta? We remember that tan is just the gradient. How would I write it? Remember, it's just rise over run.
Is it sine theta?
So rise is sine theta, run is cos theta. So I can write, that's the first most important trig identity that I want you guys to know. So trig identities, what is a trig identity when I talk about them? Like what is a trig identity? It's just a rule that is always true in terms of trigonometry. So this rule is always true. You can plug in any theta, and you can plug it into tan, and then you can plug it into sine theta and cos theta, and they will be exactly identical. It's just a rule that is geometrically true. And we know it's always true, not because we've tested it for every value of theta, but because geometrically it just makes sense. Okay? It makes sense based on all the math we know. So we know it's true. Okay? The second one is, if I just extract that triangle, and I do, this is sine theta, this is cos theta, and this is 1. Can I get, Emma, can you write Pythagoras for this triangle? What is Pythagoras for this?
Sine theta squared plus cos theta squared equals 1.
Good. That's your second trig identity. So whatever theta is, it doesn't matter what theta is. If you ever have a case where you've got sine squared theta plus cos squared theta and the thetas are the same, you can just get rid of it and say it's equal to 1. Okay? So this is the main trig identities you guys are going to need so far. When we get into the advanced trig topic, we're going to teach you guys a whole plethora of trig identities. There's like maybe 5 of them that you need. And then they become very easy to like work with. Okay? So, you guys are going to need that. I'm going to show you, it's going to be your first time seeing something like this. But just remember, it is advanced and I haven't taught it to you yet. So if it looks scary, try your best, ask questions. We can do some extra examples if you guys really need it. But don't get too scared about it. I don't want you guys to get the idea in your head that this is hard. It's not hard. It's just something new that you haven't seen before. Okay? So, essentially what we're going to have to do here is we want to kind of eliminate cos and sine. We don't want cos and sine in there because it's supposed to be a Cartesian equation, not a trig equation. Okay? So in order to get rid of them, what we want to do is we have a cos and we have a sine here. Okay? Now, what I am able to do is if I say that I just make, instead of x, I make it x squared. So I say 1 on cos squared x, or theta. And now I have 1 y equals, if I make it squared as well, if I have y squared equals sine squared theta. Okay? So now I've got my cos squared and my sine squared. Okay? Everyone agrees as long as I square both sides of an equation, I'm allowed to just square the equation. Nothing stops me from doing that, yeah? Now what I can do is I can say, well, sine squared is equal to the same thing as 1 minus cos squared theta. Where did I get that from? Well, if we just said down here that sine squared theta plus cos squared theta equals 1, okay? And we can then change sine squared theta. So we don't want sine squared theta there. We can just change it to 1 minus cos squared theta equals sine squared theta. That's just a trig identity. Everyone agrees with that? Like I just got that straight from the trig identities. So I can literally just swap this. Instead of y squared, I can just get 1 minus cos squared theta. Everyone cool with this? Now I'm going to solve for cos squared and then plug that into this equation. Everybody cool? So I'm going to solve for cos squared. So I'm going to get y squared minus 1 minus plus equals cos squared theta. Everyone cool with that? And then I'm going to plug that into here. So x squared equals 1 all over 1 minus y squared. And now you just rearrange for y. Okay? So we're going to rearrange for y. I would say in this case, so I'll just keep working down here. I get x squared 1 minus y squared equals 1. And you can just leave it in that form. Because since we have both x squared and y squared, we know that it's probably going to be a one-to-one, a many-to-many function. It's probably going to be something like a circle or maybe like an oval-looking thing. The reason they've only asked you to describe part A geometrically is because they don't necessarily need you to be able to graph this at the moment. They just need you to find the Cartesian form, okay? So remember, Cartesian form is in terms of x and y. We don't necessarily want trig functions in there. Not to say that you can't end up with trig functions sometimes, but if you get something like cos sine inverse of something, you can assume almost certainly that that's not what the answer is looking for. Even though it's not wrong, but it's not what the answer is looking for because that is definitely not a nice way to represent a function. Everyone cool with that? So if you're scared of the trig stuff right now, I remember when I first learned this, because you guys don't have the background knowledge of trig since we haven't covered trig first and then come to this. I remember when I first saw this, I was like, oh my God, every time I see a trig parametric function, my blood used to boil and I'd be like, oh my God. I promise you guys, it is not that bad. The only reason I know how to do this is because I know the trig background knowledge, okay? So what I want you guys to do, try your best to practice at least parametrics. Maybe we can stay away from trig parametrics for now. But as soon as we learn trig advanced, then I want you guys to come back to trig parametrics and be like, oh yeah, this is easy, because you guys know the advanced stuff, okay? So try your best to follow along right now, and then when I actually teach you the trig stuff, you're going to be like, oh yeah, this makes a lot of sense, okay? So that is changing a parametric equation into a Cartesian equation. Obviously, if we know how to do that, we want to do the opposite as well. We want to change a Cartesian equation back into a parametric equation. So that is what we call parametrization. We're taking a Cartesian equation and we're parametrizing it. So we're adding a parameter to it. Okay? So let's learn how to do that. We now want to learn how to convert from Cartesian form back into parametric form. So let's start with a linear example and then we'll look at circle parametrization and then parabolas as well. That is the only parametrization they require you to do in the HSC. So you only need to be able to parametrize linear, circle, and parabola. That's all you need to know how to do. So I'm going to show you each case and how to do it. Okay? So we're going to start just with linears because they're the easiest one. So linear parametrization. So in order to do this, we're going to start with... all good. So the question will be something like this. It'll say, write 3x minus 2y plus 6 equals 0 as a parametric given that x equals 2t plus 1. So they do give you some information in the question that's going to help you do this. Because obviously, if I don't give you that information, there is multiple different parametric forms of this. There's a lot of different ways you could represent this as a parametric equation. So they have to give you some kind of like information. Otherwise, you can't just randomly like parametrize something, okay? So the first thing we're going to do, obviously, we're going to make y the subject of this. Okay? So why do we need y to be the subject? Someone tell me. Because in parametric form, what do we always need? Because right now they've already given us the parametric x. We just need to find the parametric y, right? Because remember, we need to find the y and x separately. We already have the x, so the first thing we need to do is change this to give us y, and then just plug this into that. Does everyone understand? So we're just going to rearrange this for y. So we get negative 2y equals negative 3x minus 6, and then y is equal to 3 on 2y plus 3. Everyone cool? Oh, why do I, what the heck? That should be an x. Everyone cool with this? And then we're going to go ahead and plug our, is that the cleanest way to do it? I guess it's maybe a little bit cleaner if we just keep this like that for now. We'll just keep it like that. It's a little bit cleaner, but the other way works as well. They're both correct. Okay. Now we're going to sub x equals 2t plus 1. So sub in x equals 2t plus 1. Can I get you guys to do that and just simplify to the best of your ability? And then write the parametric form. Remember, to write the parametric form, you need to give me the x and y equation right next to each other just to show me the parametrization. So, let's go through this. Maybe, Emma, once you plugged it in, what did you get?
Like my final answer?
Yeah.
Y equals 6t plus 9 on 2.
I agree with that. So we expand that form and then we just get 6t plus 3 plus 6, which is 9 on 2. Okay? And then to write the parametric form, obviously, if it was a real exam style question, all I would do is I would just say, therefore, parametric form is y equals 6t plus 9 all over 2, and then x equals 2t plus 1. And if I was doing this at home as practice, I would absolutely urge you, because you've been given the Cartesian form and you have the parametric form, I would be urging you to go draw this this Cartesian form in Desmos, and then also draw the parametric form and make sure that the parametric form is tracing the Cartesian form, because if it's not, you've done something wrong, okay? So I'm going to quickly show you guys one example of that quickly now. I'm not going to be graphing every single thing in class today, but I just want to get you guys used to using Desmos, okay? So the easiest way to graph a parametric would probably be to go to my Desmos link here. It would be great if it was an actual link and you didn't have to copy paste it, but pretend you click my link and then you end up here in Desmos. All you need to do is just change some things. So you found your parametric x. So my parametric x was, where am I? 2t plus 1. So I'll just write that down, 2t plus 1. And then my parametric y was 6t plus 9 on 2. So 6t plus 9 on 2. And then I also want to graph my Cartesian form, and I'm going to add a slider for t. So the easiest way to get a slider is just write like a capital letter and then write t in brackets. And it'll give you the option to pop up a slider and then just get rid of the ones you don't want. So I just want my t slider, okay? And then the other thing you're going to do is graph the Cartesian form. So my Cartesian form is 3x minus 2y plus 6 equals 0. So I'm going to just graph that. 3x plus 2y plus 6 equals 0. And that should graph a nice line for me. Now, already something is looking bad because my t is not at all doing what it's supposed to be doing. So I'm believing that we've done something wrong here. Let me just double check. No, we haven't. I just typed my Cartesian form wrong, so that should be a minus. Cool. And we can see that my parametric form is indeed tracing my Cartesian form, which is awesome. Okay, so that's exactly what we want. Please make sure that you guys are actually going on Desmos and doing this. It is going to increase your understanding tenfold when you just play around with things yourself at home, okay? If you don't play around with it, you're just always it's just like writing numbers and you don't really know what you're doing. And obviously that's going to stop you from being able to answer the harder understanding questions. Okay, so being able to visualize stuff, because humans are visual learners, absolutely go on Desmos and do this. Also, it's pretty cool. Like, look at you making little animations on Desmos. How cool. Okay, so yeah, that's the linear parameterization. Any troubles there? I think linear is quite easy, right? It's literally, again, just the opposite of what we did before. The next one is a little bit harder, which is circle parameterization, and you guys are gonna love this, involves trig. So let's do that, and then hopefully I can get you guys to understand it. So let's do it. So circle parameterization. The way we're going to learn this, we're just going to start again with a unit circle. So instead of a unit circle this time, we're going to just start with any circle with any given radius. So we're just going to call the radius r for whatever it is. So we'll just call it r as the radius. Now, I want to go back to my trig thing here. You know how cos theta sine theta was my point if radius is 1? Yeah? What if the radius is bigger than 1? So for example, what if my radius instead of 1 becomes, I don't know, like 2, for example. Becomes 2. So what if I make like a bigger circle like this? Do we all agree that it's still going to be cos theta sine theta, but it's just going to be scaled up? So if you see, my sine theta used to be this, but now I want it to be this. So it's just kind of like times 2 to my sine theta because we've increased the radius to 2. Okay, so whatever your radius is, you can treat it as like a scale factor. It's just scaling up your cos and sine. Okay, so same thing here. Instead of cos theta sine theta, we're just going to write r cos theta to scale it up, and then sine cos theta. Sorry, r sine theta. Everybody cool with this? And that'll be our theta there. Does anyone have any trouble with that? Is anyone confused about why I've labeled it r cos theta and r sine theta? Does everyone get why I have the r there? Tariq, do you get it?
Yes.
Okay. So now, we can safely agree that my x is just equal to r cos theta, and my y is equal to r sine theta. Now, the whole point of a parametrization is that I just want to be able to write a formula for x and a formula for y. Have I managed to do that here? I have. I've managed to write a formula for x and a formula for y. And we just need to remember to include a range. Can theta be whatever we want it to be? It can, but in order to, because like the whole point is that if we let theta go on for infinity, then we're going to just be drawing multiple circles over it themselves forever. So it's good to involve a little region for theta, and we'll just say that it's between 0 to 2 pi. Remember, 2 pi is a radian. I feel like were you here for the radians lesson?
I was on one.
Okay, so if you guys just remember what 2 pi means, it just means 360 degrees. It's just pi is half the circle, so 2 pi is a full circle. So all you've said is you're restricting theta to say that, you know, we're just going around the circle once as part of our parametrization. So we're just, if you guys imagine the Desmos animation, it would just go like that instead of just like the circle keeps, the point keeps going around and round and round. We're just going around once and that's it. Everyone cool? Now, what if, so that's a circle at the origin. What if I move my circle? So what if I just have the exact same thing, but I now want to parametrize a circle that's like maybe somewhere here. So I've just moved my origin. Let's say my new origin is at HK. All you need to do, you're going to just use some graph transformations for this. So my x is r cos theta as normal. But Emma, can you tell me what have I done with x?
I did x minus h.
Yeah, so it's just literally x minus h. But so it's x minus h, but then we move the h to the right hand side, so it becomes x plus h. Everyone agrees with that? And then Tariq, with my y, what have I done with my y?
Plus k, minus k.
Minus k, so I've done y minus k, because I've moved the axis down, so the graph has moved up. And you guys can kind of visualize that, right? You can see the axis has moved down, so the graph has moved up. But then obviously we just want to get y on its own, which is why we move the k to the other side. So it just becomes y plus k. Everyone cool with that? So this is a circle parametrization, and it's nothing too crazy, right? Everyone agrees this is like quite simple, yeah? And again, we can limit the angle to 2 pi. You don't absolutely necessarily have to limit it, but it is good to limit it just to show like that's the parametrization, but you don't have to in the question unless it asks you to. So if the question says like with theta between 0 and 2 pi, you just need to make sure to write that in your parametrization. Okay? So I'm going to give you guys a little example to try for circle parametrization. Can I get everybody please to find the equation of x equals -4 plus 3 cos theta, and then y equals 5 plus 3 sine theta. So this is not a parametrization, this is the opposite. We're going back into Cartesian form. And the way I'm going to get you guys to do this is remember something very important, that sine squared theta plus cos squared theta equals 1. Can you guys figure out how to work with both of these equations simultaneously to somehow, some way, end up with a cos squared theta and a sine squared theta that you can add together? My hint is going to be rearrange the first equation for cos, rearrange the second equation for sine, and then go from there. Okay? So I'll get you guys to try that now. Alright, so let's go through this one. So as I said, we want to somehow end up with the sine squared cos squared equals 1. So what we can do, the easiest thing, solve this for cos squared, for cos. So we get cos theta is just equal to x plus 4 on 3. And then square both sides. Everyone cool with that? Same thing here. Sine theta is just equal to y minus 5 on 3, and then square both sides. Now we can add the equations together. So if I add them together, I just end up with cos squared plus sine squared, which is just 1, is equal to x plus 4 on 3 squared plus y minus 5 on 3 squared. And you can just kind of stop there. The reason you can stop there is because this is now just a circle equation, and you don't really need to simplify circles. It's not actually a circle. Oh, it might be a circle. It is a circle. It is a circle, but if one of these numbers were different, it would then be an oval. Because when you like divide, you guys can imagine, if I have a circle and then I dilate only the x, then I'm going to end up with an oval. So if I dilate only the x by 3, then I'm going to end up with a thin oval. So the y's don't dilate, but the x's do. But then if I also dilate the y by 3, then I end up with just a smaller circle. Everyone cool with that? All right, nice. And if you really, really wanted to, you can change the radius by expanding this. So you could do something like this. So how did I know? You know how I just drew that when you dilate both, the radius just gets smaller? Or in this case, it would actually get bigger because we're shrinking the axis, so the radius is getting bigger. The way that you can show the radius is getting bigger, perhaps would be to do something like this. X plus 4 squared plus y minus 5 squared is equal to 1 times 9, because 3 squared. So it just becomes 9. So the radius just gets bigger. Everyone cool with that? You can even write it like 3 squared to be extra clear that it's a circle. Okay, so that's how to parametrize a circle. So this is how to parametrize it, and then we just did another example of rearranging it into a Cartesian form. And everyone can see that the original question that I gave you was in the form that we expected of a parametric, right? So does everyone agree that this circle is not centered at the origin? And so it was in the form that we expected. It has like the plus h and plus k, and then it also has the 3 cos theta, 3 sine theta. Everyone's cool with that? All right. Let's do the last thing, which is parabola parametrization. And then we've finished parametrics, and then we'll do some examples, and that's all for today. We've been moving quite fast. We've been finishing about one topic every lesson, which is awesome. Okay, so let's do parabola parametrization. So To parameterize a parabola, it's kind of the exact same thing as linear. Okay, so really the only time it gets a little bit confusing is when we're dealing with trigonometry, which is only when we deal with circles. Okay, we can even see that this example we did before, we ended up with a circle adjacent thing. Okay, so parabola parameterization is very easy because there's no trig involved or anything. It's just like normal algebra. So parametric form of a parabola is dependent on parametric form of parabola is dependent on the Cartesian form. Which is x squared equals 4ay. So we want to be able to put the Cartesian form in that equation style. So for example, let's say that we have x equals 2at and then y equals at squared. So this is just a general form. I'm not doing an original, like a actual question. But what I want you guys to realize is that this Cartesian form is the general Cartesian form that you'll require to be able to parameterize. So I'll show you guys an example of how we would do this. So it'll make more sense when I do show an example. So bear with me for a moment. Let's say that we have this. And we want to make it parametric. The way we're going to do that is we need to start by putting this Cartesian form into this general formula. Okay, so we're going to try and isolate the x squared. So I'm going to end up with x squared is equal to negative 8y. And then I want to do it even further by making it into a 4ay. So x squared is equal to 4 times negative 2y. So everyone agrees my a is negative 2. Yeah? And so now all I have to do is I literally just have to plug this into this. That's it. So my x is just 2at, which is 2 times negative 2 times t. And my y is just at squared. So it's negative 2t squared. And then I'll just simplify. So I get negative 4t and I get negative 2t squared. Okay? And I'm just teaching it to you guys very roughly like this right now. But next week I'm going to show you a proof for this. But the only reason I'm doing it so quickly today is just because I want you guys to be able to do questions when you go home this week. But next week I'm going to show you guys the actual proof for this and why this is the general form, because it's obviously different than anything you've seen before. So let's do an example. Can I get you guys to write the parametric form of y equals negative 16x squared using p as your parameter? So everyone go ahead and try that. So the same thing, you just need to start by putting it in this form, and then this is your general equation. So that's, as long as you start by putting the Cartesian form like this, and I might make it extra clear for you guys. So this is the Cartesian form. And then this is the parametric form. Everyone cool with this? So go ahead and give that a go, and then we're gonna talk about homework for the week. So let's go through this one, and then we're gonna talk a little bit about what I'll set for homework. So parametric form. First of all, what's the Cartesian form you have to put it in?
X squared equals y.
Yep. So what did you make it? X squared equals what? So it would be like negative y on 16, yeah? And so that's just x squared equals 4 times what?
Negative 1 on 64.
Negative 1 on 64y. Yeah, I just want you to break it up in that way so you know like what the thing is. And then now we just write the parametric form. So x is equal to 2 times negative 1 on 64t. And then y is equal to 2 times, sorry, not 2, negative 1 on 64t squared. And so then we simplify that, and we're just going to get 2 on 64 is 1 on 32. Is that right? So x equals negative 1 on 32t, and then y equals negative 1 on 64, or we can just write t squared on 64. Okay? And again, please do not forget, guys, when you're doing this at home, especially because it's the first week you've been introduced to it, and I really want you guys to like get a really good visual understanding of parametrics, please go graph this on Desmos. Okay, so all you need to do is just graph this function and then also graph these two functions. So for the last time, I'm going to show you one more example of this, just so that everyone has it in their brain how to do it. So what I want you to do is I want you to compare the Cartesian form and the parametric form that you got. So we're going to start by comparing the Cartesian form, and in order to do that, you're just going to write the Cartesian form. So y equals negative 16x squared. So y equals negative 16x squared. Okay? Then you're also going to write the parametric form. So you're going to write your x was negative 1 on 32t. Okay? And the other thing, guys, is the reason I also want you to do this is because I don't just want you to listen to what I'm saying. Like, I just taught this to you, and you have no idea where it came from because I haven't showed you the proof yet. For all you know, I could be making shit up in my out of my ass. You'd hope I am not doing that, but I could be. Okay? It's good to check things to make sure that not only I understand them and I know they're true, but you guys should know they're true as well, because you should see with your own eyes that it's true. It's like kind of the whole like, trust me, bro, I'm right. What if I'm shit at math and you guys just don't know? You know what I mean? So please make sure that you don't ever just like take what someone tells you as proof in math. It's really good to have your own mind and your own understanding, because it just means that you know the math yourself instead of relying on someone else to know it for you. Okay? So the last one is y equals negative 1 on 64t squared. Negative 1 on 64 t squared. Cool. And so now we have our little parametric form here, and we're finally just going to play our t. And we can see it indeed does follow, and obviously you can make these much wider. So we can make it like 100 and 100, and the step just makes it go faster. So I might make it a step of 5, just so we can see it go a bit faster. It's not playing. I think it's like, what is happening? Maybe I don't want to step of 5. I don't know. No, it's just glitching out because I've given it too much to do. You can just drag it. Oh, no. Girl has glitched. Let's just make it 50. Maybe I'm asking too much of Desmos. No, I think my Desmos has actually just crashed, so whoopsies. Maybe I'll put it back at 10 and see if that works. No. My Desmos has crashed, so sorry about that. Maybe if I don't try playing it, so maybe if I just do 20 and negative 20. Oh, I know what I was doing. I was making it 20 and 20, so there was only 1 point. So I should have been making it negative 20. So never mind, my Desmos hasn't crashed. I'm just an idiot. See, guys, don't trust me. But yeah, we can see it is indeed correct. Okay? And then next week I'm going to show you guys the proof as to like where the hell this random thing I showed you came from, because I did kind of pull a formula out of my ass and did not tell you where it came from. So that is bad. I will show you where it comes from next week. Okay? And you guys can do a little bit of your own research about it too. You can literally, it's just called parabola parametrization. You guys can watch a video about it. It's pretty straightforward if you're interested. Okay? So this Desmos link has been given to you. I will save this just so that's saved. So that link will now send you to this graph instead, just because it's a bit more, it has the t, so you guys can play around with the t, and it also has the like Cartesian form as well. And I might even edit it for you guys a bit further. I might just add a note that this is the parametric form. This is graphing the parametric form. And then this is your Cartesian representation. Okay? Just to make it representation. Just to make it extremely obvious for you guys. So that's saved now, so it just has a bit of notes there as well for you, just so you know what's happening everywhere. Okay? So for homework, I'm literally just going to set you guys a textbook chapter about parametrics. Please make sure you guys do it, and as Emma, you did this week, please keep asking questions. Very good to ask questions. Make sure you guys do those textbook questions. They are very important, although they're not exam style questions, and obviously exam style questions are the most important thing you guys are going to be doing. I do want you guys to do the textbooks just because they have like very abstract questions that you maybe wouldn't get asked in an exam, because sometimes the question will require you to like play around with Desmos, draw some graphs and stuff, but they do increase your understanding. So the whole point of textbook is to kind of like form the connections in your brain that like this is what's happening. And then exam style questions obviously are designed so that they can be very quick to solve, but they're only quick to solve if you know what is happening. So the only way you can be really good at the exam stuff is if you do the textbook stuff, because it's kind of like the background knowledge you need. Okay, so just going to the syllabus quickly before you guys head out. We've done all of this, but I'll just tick it off for you guys. So recognize that a curve can be represented by two parametric equations that give x and y as a function of a parameter. I think we all understand that. So the x and y coordinate are separately represented in terms of a parameter. Express linear, quadratic, and circles in parametric form. So again, that's all you need to know how to do. Okay? You don't need to know cubics, you don't need to know polynomials, you just need to know linear, quadratic, circle. And then convert linear and quadratic functions and circles from parametric back to Cartesian. I think we all know how to do that now. And then graph linear, quadratic, and circles expressed in parametric form. So how would we graph them? Obviously, you can't graph them when they're expressed in parametric form. So step number one would be convert to Cartesian form. And then from advanced math, we all know how to graph linears, circles, and quadratics. Okay? So that is all. That's all of parametrics. So next lesson, we're doing inequalities, and then we're completely done with functions. I will, for this year, probably start trigonometry for advanced math. I'm only going to do trigonometry for advanced. I won't go into the extension stuff this year, so that'll probably be to the end of the year. You guys would have covered 2 of the advanced math topics and 1 of the extension math topics. But the reason I'm not going to do more than that, not because we won't have time, we probably will have a little bit of time to go through the extension stuff, but I want to give you guys the opportunity to study over the holidays. Obviously, I know it is Christmas and whatever, but after Christmas is over, I would really like to see you guys studying this stuff, because functions is your first exam. So in your first exam, you will not have trig, and you will not have anything else in extension as well. The stuff I've taught you so far is your first extension and advanced exam, okay? So I want to give you guys the opportunity to study, because obviously your exam is probably not for another, I don't know, like 3 months. If you start studying from now, you are literally, yeah, probably 4 actually, because it's in like, it'll probably be like week 10 or something of term 1, which is like about 4 months away, which is almost close to a quarter, like more than a quarter of the year, right? You have a quarter of a year to study for this one tiny topic test. You guys can absolutely get 100% in this topic test if you start studying now. That means going home, making sure that as part of your homework, this is homework for every single week, you guys are doing advanced tests, and you're also doing extension tests starting from next week as soon as I finish inequalities, okay? And I'm going to try to keep filling the drive folders with as many questions as I can, so you guys never run out of exam questions. Alrighty, I will see you guys next week.